Something has been hiding in plain sight for 4,000 years, not buried under sand, not locked inside a tomb, not encoded in hieroglyphics waiting for a linguist to decode it. It has been sitting in the corners of the most photographed structures on Earth, in the precise 90-degree angles of the Great Pyramid of Giza, angles so accurate that modern engineers using laser theodolites and GPS calibrated instruments have measured them and found an error margin of less than 1/20th of 1 degree. Let that land for a moment. The people who built these structures did not have computers. They did not have steel measuring tools manufactured to micrometer tolerances. They did not have the mathematics textbooks that took humanity another 2,000 years to write. And yet they achieved a geometric precision that a significant number of modern construction projects, built with all of those advantages, quietly fail to match. For centuries, historians called it a mystery. Archaeologists called it remarkable. Engineers called it improbable. And everyone more or less agreed that while we could admire what the Egyptians built, we might never fully understand exactly how they did it with the tools they had. Then someone decided to ask an AI. Not just any question, not the vague, hand-waving kind of prompt that produces a confident-sounding paragraph of mush. A researcher sat down with Grok, the AI system built by XAI, Elon Musk's artificial intelligence company, and asked it to do something that no tool had quite been able to do before. To take everything humanity knows, every archaeological record, every ancient text, every experimental archaeology study, every mathematical analysis, every scrap of surviving evidence about how ancient Egyptians worked with geometry, and synthesize it into a coherent, testable, mechanically plausible answer to one of the oldest open questions in the history of human civilization. How did they make perfect right angles? What Grok produced wasn't a guess. It wasn't a theory pulled from thin air. It was something closer to a structured reconstruction, a working hypothesis built from converging lines of evidence that had always existed but had never quite been assembled in the same room at the same time. And when you see what it found, when you understand the elegance of the solution that was apparently available to ancient Egyptian builders using nothing more than rope, stone, and a knowledge of numbers that predates Pythagoras by over 1,000 years, something happens to the way you think about intelligence, about history, about what it means to understand a problem, and about what AI is actually capable of when you point it at the right question. Let's start with why this problem is harder than it sounds. When most people think about making a right angle, they think about a set square, that triangular plastic tool from school geometry class, or they think about a carpenter's square, the L-shaped metal instrument that sits in every hardware store in the world. Both of those tools work by the same principle. They are rigid objects manufactured with a 90-degree corner built into their physical form. You press the corner against your work, and the angle transfers. Simple. But now imagine you are standing in the Egyptian desert approximately 4,500 years ago. You do not have precision machined metal. You do not have plastic. You do not have a factory or a tolerance standard or a quality control process. You have stone, wood, copper, and rope. And you are about to begin laying the foundation of a structure that will cover 13 acres of ground, rise to a height of 481 feet, and be required to sit with such geometric accuracy that its four base corners will form right angles precise enough to satisfy a modern surveying standard. How do you even begin? This is not a question about ambition. The Egyptians clearly had that in abundance. This is a question about method, about the specific physical process by which a human being, standing on flat desert ground with the tools of the ancient world, can verify and enforce a 90-degree angle across a distance of hundreds of meters. It is a question that has attracted archaeologists, mathematicians, experimental historians, and engineers for generations. And it is a question that, until recently, had several competing answers and no consensus. The most commonly cited explanation involves what historians call the 3-4-5 triangle. Here is the mathematics. If you take a right triangle, a triangle with one 90-degree corner, and measure its three sides, those sides can never be just any three numbers. They are constrained by a relationship that Pythagoras would later formalize, but that the Egyptians appear to have known empirically centuries earlier. The square of the longest side, the hypotenuse, always equals the sum of the squares of the other two sides. And one of the simplest whole number combinations that satisfies this relationship is 3, 4, and 5. A triangle with sides of 3 units, 4 units, and 5 units will always have a perfect right angle between the 3-unit side and the 4-unit side. Always. Without exception. It is not an approximation. It is not close enough. It is exact, built into the mathematical structure of Euclidean space itself. The theory goes that Egyptian builders knew this, that they used knotted ropes tied with equally spaced knots, to form these triangles on the ground. A rope with 12 equally spaced intervals, when formed into a triangle with sides of 3, 4, and 5 intervals, produces a guaranteed right angle that can be transferred to any construction site regardless of scale. The people who performed this work are even referenced in ancient Egyptian records. They were called harpedonaptai, a Greek term meaning rope stretchers. Their existence is documented. Their role was geometric. The rope triangle theory is elegant, historically grounded, and widely accepted among Egyptologists. But here is where it gets complicated. And here is where Grok's analysis begins to diverge from the standard textbook answer in ways that are genuinely illuminating. When the researcher pushed Grok to go beyond the 3-4-5 triangle and examine the full body of evidence, something interesting emerged. Not a contradiction of the rope triangle theory, but a layering of it. A recognition that the precision achieved at Giza and other major Egyptian construction sites was almost certainly not the result of a single technique applied once at the beginning and then trusted forever. It was the result of a system, a redundant, cross-checking, iteratively verified system of geometric control that combined multiple methods, each one serving as a check on the others, so that errors introduced at any single step would be caught and corrected before they could propagate into the structure itself. This is a sophisticated engineering insight, and it is exactly the kind of insight that becomes visible when you stop looking at individual pieces of evidence and start looking at the whole picture simultaneously, which is precisely what a well-directed AI system can do in a way that no single human researcher, constrained by the limits of time and memory and disciplinary specialization, can easily replicate. A vertical rod planted in level ground, what the Greeks would later call a gnomon, casts a shadow that moves in a precise arc through the day. In the morning, the shadow points in one direction. In the afternoon, it points in another. At the 2 moments when the shadow is exactly the same length before and after solar noon, it points in directions that are mirror images of each other around the true north-south line. By marking both shadow tips and bisecting the angle between them, a builder can establish true east and west with no astronomical instruments, no star charts, and no complex calculations. Just a stick, a level surface, and a way to measure shadow length. Grok's synthesis highlights something that individual analyses of this technique often underplay. The shadow method and the astronomical method are independent of each other. They are based on completely different physical phenomena, the movement of the sun versus the position of the stars. And yet, when applied correctly, they converge on the same answer. This is not a coincidence. It is the signature of a truth about the geometry of the Earth. And for an ancient engineer, the fact that 2 completely different methods of establishing direction gave the same result would have been a powerful form of verification. Not just a technique, but a proof. The third layer is where Grok's analysis becomes most fascinating, because it involves a piece of evidence that most historical accounts treat as a minor footnote, but that the AI identified as potentially central to the whole system. In the collections of several European museums, there exist ancient Egyptian artifacts that archaeologists have classified as set squares, L-shaped or triangular wooden and stone tools clearly intended for measuring angles. The existence of these tools is not controversial. What is less well understood is how they were made, how they were calibrated, and how their accuracy was verified and maintained over time in a world without reference standards. Grok, drawing on experimental archaeology studies and analyses of surviving artifact dimensions, synthesized an answer that is surprisingly elegant. The tools were not the primary source of the angles. They were derived from the angles. The process likely began with the astronomical and shadow methods establishing a true right angle at a large scale in the open landscape. That large-scale right angle was then used to construct and verify the wooden and stone tools that builders would carry and use at the scale of individual stones and joints. The tools were calibrated against reality, against the geometry of the earth and sky, not against each other. This is crucial because it means errors could not easily compound. Each tool generation was re-verified against the master reference rather than copied from the previous generation of tools. It is, in modern terms, a traceable calibration chain, the kind of quality control system that precision manufacturing industries would not formalize until the Industrial Revolution. And then there is the fourth layer, the one that Grok surfaced from the intersection of materials science, archaeology, and practical geometry in a way that feels almost counterintuitive until you think it through. It involves water. The Egyptians were extraordinarily skilled at using water as a leveling instrument. Channels cut into the bedrock of construction sites, channels that have been found and documented archaeologically at multiple pyramid sites, could be filled with water to establish a perfectly level reference plane across large distances. Water finds its own level. It does not care about the imperfections of the ground beneath it. It does not accumulate measurement errors. It simply seeks the gravitational equipotential surface, the same surface that defines sea level, and in doing so, it creates a horizontal reference of essentially perfect accuracy over any distance you care to work with. What Grok did with this question was not magic. It was not intuition. It was not the sudden inspiration of a genius. It was something more systematic and in some ways more interesting than any of those things. It was the application of a tool that can hold an enormous amount of human knowledge in simultaneous consideration, identify connections between findings that exist in separate disciplines in separate centuries, and synthesize those connections into a coherent framework that no individual researcher, no matter how brilliant, could easily assemble alone. An Egyptologist knows the rope stretchers. A materials scientist knows the properties of limestone and how it behaves when shaped with copper tools. An astronomer knows the stellar alignment theories. An experimental archaeologist knows what happens when you try to build a large structure using ancient methods and where the practical difficulties actually arise. A mathematician knows the properties of the 3-4-5 triangle and its relationship to Pythagorean triples. And a hydraulic engineer knows exactly how accurately water channels can establish a level reference over a large area. Grok knows all of these things at once, and when you ask it the right question, it can draw on all of them simultaneously in a way that reveals the integrated system behind what looked, from any single disciplinary vantage point, like a collection of interesting but separate observations. This is what AI is beginning to do for human knowledge, not replace the experts, not make the archaeologists and historians and mathematicians redundant, but serve as a kind of connective tissue between fields of inquiry that have for too long existed in isolation from each other. The history of human civilization is stored in millions of books, papers, records, and artifacts scattered across hundreds of languages, disciplines, and institutions. No human being can read all of it. No team of human beings can synthesize all of it, but an AI system trained on a significant fraction of that knowledge, directed by a thoughtful question and guided by a researcher who knows what they are looking for, can begin to see patterns in the whole that are invisible from any single part. And what those patterns are revealing about the ancient world is not, as some might fear, a story of demystification. It is not the AI arriving to explain away the wonder of what the Egyptians achieved. If anything, it is the opposite. Because what emerges when you understand the full system, when you see the astronomical observation feeding into the ground level reference, feeding into the calibrated tools, verified against the water channels, cross-checked by redundant methods drawn from independent physical phenomena, is not a picture of a primitive people using a clever trick. It is a picture of a sophisticated engineering culture that had developed, through centuries of accumulated practical knowledge and empirical testing, a system of geometric control that was robust, self-correcting, and capable of achieving results that still command the respect of engineers today. They did not have our mathematics. They did not have our instruments. But they had something that is, in many ways, more impressive than either of those things. They had a deep, practical, hard-won understanding of how the physical world behaves, and they had organized that understanding into a coherent system of practice that could be taught, transmitted, refined, and applied reliably across generations and across the enormous logistical complexity of a major construction project. That is not primitive. That is not lucky. That is engineering, real engineering, the kind that works. And there is one final thread in Grok's analysis that deserves its own moment of attention, because buried in the synthesis of all this historical and mathematical and archaeological evidence is a question that points forward as much as it points backward. The methods the Egyptians used, the astronomical reference, the shadow square, the plumb line and water level, the rope triangle, all of them share a common characteristic. They derive their accuracy from physical reality itself rather than from manufactured instruments. The star does not care about the limitations of the tool that observes it. The water does not care about the imprecision of the channel it fills.